This talk is about trust in named data networking, and if you don't know what named data networking is, I'll tell you. It's joint work with one former PhD student who is now at Xerox PARC, and one of my current PhD students. So I'll tell you a little bit about named data networking, and this actually not a little bit, a lot, because in order to tell you anything about security of that something, I have to tell you about something first. Right? So I need to introduce you to that, and that might take a bit of time. And then the more technical part of the talk is the last two bullets. So let's jump right in. I'm sorry if you already know what context-centric or named data networking is. This will be boring for you, this part. So for God knows how long, maybe 150 years, maybe longer than that, communication meant a wire or a virtual wire connecting two devices or two interfaces like this, and from telegraph all the way to today's internet. And the web, not the internet, right? The web in mid-90s changed that seemingly forever. And it changed it in a way that took the emphasis from the endpoints of communication to the content of communication, right? So what becomes more important with the web, or what became more important with the web, is information, right? Information rather than the place it came from. Okay, that's one of the foundations or one of the bases for this whole concept of named data networking. And as you know, I'm sure you all know, that today's internet is a tremendous success, right? It's hard to compare it to something, right? It's a one of a kind. It's the first of a kind. It lasted longer than anybody would have anticipated. It served bigger purposes, wider range of solved wider range of problems than anybody could have thought of in early 80s or late 70s when it was originally when most of you weren't born and it was originally designed. Yeah? So the architecture is defined in two RFCs, and 791 and 793, and they date back to 1981, which is very, very, very old by today's standards, right? So in particular, IP, right? TCP is not the internet. What really defines the internet is IP. It is the Esperanto or lingua franca of the internet. It is a protocol which is and format which is surprisingly simple and enables any host or any interface to talk to any other interface in the world. I guess I haven't turned on my microphone, have I?
Yeah, no problem.
Oh, it's on?
Yeah.
Okay. It assigns names and addresses to boxes being some kind of computer, right? From very small to very large. And every computer is assumed to, that is on the internet is assumed to have an interface. So if it has more than one interface, it can have more than one name. It supports end-to-end conversations between two interfaces and provides famously unreliable packet delivery via so-called IP datagrams with very simple headers. And the simplicity of IP, simplicity and flexibility of IP, is compensated by impressive complexity of TCP at the endpoints. Right? So reliability, if it's desired, needs to be compensated by this complexity. And so if you've ever taught a networking course, or if you've taken maybe a networking course, you know that IP is easy to explain. You can probably do it in 30 seconds to a reasonably apt E or CS student. Whereas showing somebody a state diagram of TCP can cause immediate headache. Yeah? And it's not something one can get quickly. So that's today's internet. It inadvertently helped facilitate and triggered today's web, right? Today's world of content. I think the world today is not endpoint-centric anymore. As I tried to make the point earlier, the world of the internet today is mainly information-centric. So the internet of 1980s kind of helped create the world of content we live in today, but was not actually designed for it. Right? It's as if you build highways and all of a sudden, you know, people will start driving tanks on them. Well, the highways will hold up for a bit, but after a while the tanks will probably destroy it. So far, so good, right? We haven't seen any catastrophic events. We haven't seen the internet fall to pieces because of the world of content that we're living in. But one of the arguments towards creating new internet and exploring new internet architectures is the fact that today's internet is creaking, you know, like an overloaded ship or a container. It's kind of approaching the limits of its lifetime. And so whether it will happen tomorrow or 5 years from now, it's good to be prepared. So again, the central abstraction of the internet is a host identifier corresponding to an IP address. Let's keep that in mind. So as I said, the world of content, right, is what we live in today. Back when internet, well, ARPANET was first created, the people who designed it were envisioning let's see, mainframe computers connected to terminals, right? A few mainframe computers capable of performing high performance computation, et cetera, like climate simulations and models and various physical phenomena, and basically doing lots of number crunching. And because these things were massive and expensive, people needed to connect to them from around the world, remotely. Connect to them via terminals. PCs did not exist. Okay? That was the raison d'etre for the internet. Well, and then it helped to, of course, have email. So email is one of those things that's still there, still accounts for some tiny percentage of bandwidth on the internet, probably will not go away for a while. But things like FTP and Telnet, they're largely gone. Or at least they don't account for much of anything. But the shift has transpired from this kind of email FTP Telnet, or Telnet was the way to access remote computers, right? Remote resources. FTP was a way to transfer large files, point to point. But now we have this massive content distribution network. Most content that's generated on today's internet, from Twitter, from little Twitter missives all the way to very large videos, okay, is consumed by more than one person, by more than one entity, which is very different from what used to be the case. And one way to look at today's internet is that it is essentially a communication network that is being used as a distribution network. Now, to define to make a distinction between these two terms, what is a communication distribution? So the communication network is the one where the central abstraction is the endpoint, right? And that communicating endpoints, that kind of a network has no memory in it. Two endpoints communicate, and what matters is that the pipe between them, right, that connects the two endpoints, and everything comes out of the right pipe, and therefore it's trusted and it's good, et cetera, et cetera. So in that kind of a communication world, where the network itself has no memory, and the central abstraction is the endpoint, security implies the communication process itself, right? So you secure the process like we do today with SSL TLS or IPsec, right? Point-to-point, end-to-end security. Whereas in the distribution network, where the central abstraction is not the endpoints, but rather the content or information that is being distributed, it doesn't, the endpoints kind of fade into the background. And the network starts acquiring memory. And so now the storage and wires kind of mesh together. There is no longer a distinction between storage and communication itself. And security then is focused on not the endpoints, but the information or content that is being distributed. Now, some number of years ago, about 6-7 years ago, the National Science Foundation, which is the premier funding organization in the United States, decided, with help of some advisory board, to start a program called Future Internet Architecture. Right? So realizing that today's internet is kind of approaching its limits, they ran this program, and it's a kind of a one-time program, not a recurring one like most of the others. And after 2 or 3 levels of elimination, they selected 4 projects. The 5th one was added later, and they're listed here. And if you do a quick Google search, you'll find all of them. So I don't put pointers here. Mobility First is the one headquartered, ran by, Rutgers and a bunch of other universities, but led by Rutgers. XIA, or XIA, is CMU led, but involves other universities. NDN is the one I'm going to be talking about. ChoiceNet is NC State, North Carolina State, added later. And the 5th one is Nebula, and that's University of Pennsylvania. All very different, all distinct. So they share some features, but emphasize different things. All aimed at the next generation, or candidate next generation internet architecture. So what is, say, named data networking, or NDN? If you've ever heard of something called CCN or ICN, Information-Centric Networking or Content-Centric Networking, NDN is an example of that kind of networking. It targets one thing: scalable content distribution. So not email, not mobility, not space communications, not underwater communication, not pigeons, scalable content distribution. Under the assumption that that kind of content distribution is not served well by today's internet. And these are the players. Actually, the list is a little longer now because the project ended its first phase and began its second phase, and a couple of other entities have been added to this list of participants. Most of these are universities except for PARC, which is a research center. But UCLA is the lead institution. So let's, since the subject of this talk is trust, more generally security and privacy, let's switch to that, or focus on that. So for those of you who do know how the internet ticks, it's not a surprise that security and privacy is not a success story. Right? The internet itself is great, and we can all marvel and wonder how it survived this long and this well. But security and privacy part of the internet, of today's internet, is not a great success. And we have actually nobody to blame for it, right? Why? Because, well, the good people who brought us the internet of today were envisioning a much different world. They never fathomed millions and millions and billions of people using the internet. They envisioned a world where a bunch of well-meaning and relatively benign academics and a few government agencies would be exchanging information and sharing resources. Kind of a world where you essentially sit around campfire and sing Kumbaya and pass around a nice beer. They did not envision the hostile world we live in today and the scale that we have today. So we cannot blame them for not worrying about security at the time. Also, they had no idea it would last that long. So, but what we have today, as far as security and privacy on the internet, is a hodgepodge of retrofitted, poorly fitting Band-Aid style solutions, including clunky IPsec and SSH and TLS this and SSL that and HTTPS. And not I'm not saying that any one of those is particularly bad. It's just that they were designed to solve a specific problem. They were not designed to address security or to address privacy. They were designed for a specific protocol, essentially as a patch. So, and there are others. So, in its wisdom, and I don't mean this sarcastically, National Science Foundation said, well, if you're going to propose a candidate internet architecture to replace the internet of today, you better address security and privacy from the start. That was wise, right? That was wise. So every team of the 5 that I mentioned, every single team that was funded had to have security and privacy people in it among its members. And so that's a good thing, right? And so the privacy and security are important from the beginning. And to this end, if you look at all of these architectures, they all have prominently privacy and security features. Now, of course, to what extent they're effective differs, but they all have some. All right, so let's go back to switch to NDN. Okay? So today, as I said, NDN emphasizes scalable content distribution. So today's internet, when the next, I don't know, gravity challenge lady in Scotland decides to sing her heart out, or somebody's kitten decides to bark like a dog and somebody posts a video, or when another spectacular, God forbid, terrorist attack happens and some moron, films somebody getting their head cut off, like, for better, like bees and honey, people tend to assault, the source of that content, right? And what happens is, if it's YouTube, could be any other site, but if it's like YouTube and everybody wants to come to YouTube to fetch a particular video, well, then YouTube winds up serving every request separately. Okay? Now, of course, I'm exaggerating. If you are YouTube or a large, rich content provider, the picture probably is a little different. Do you know why? Anybody know? CDN. Yes. We have CDNs like Akamai. And so what Akamai does is it places nodes at the edge of the internet and tries to solve this sort of scalability problem, right? So that not all requests come into and emanate from YouTube, but rather they go to various geographically distributed CDN nodes. Now, not everybody is rich enough to be paying Akamai or its competitors. One. Two, CDN is at the edges of the internet, at the application layer, right? As an overlay. So CDN does not permeate the internet architecture. There is no such thing as CDN at the network layer. Okay? So that results in suboptimal communication and a lot of wasted bandwidth, and therefore congestion. So this is how content distribution would look with NDN, or any kind of content-centric network, not just NDN. You see, the idea is that if you have a massive, near simultaneous onslaught of requests for the same content, what would happen is a provider like YouTube would get an initial number of requests coming from incident links, right? From adjacent links. How many requests? Exactly as many requests as there are incident links, which means that the initial wave of requests would be still quite small. Once that wave of requests is satisfied, what would happen is that routers would cache all content that is forwarded out. Consequently, all other requests will be served from the network rather than from the source of content. So I think you get the idea now, right? Now this has some immediate connotations. I'm sure if you are a networking person, you immediately think of some good things and some terrible things. Okay? So we'll probably touch upon many of those. So at the foundation of NDN, or one of these basic tenets, is the notion of a human readable name. So that means that every content, every piece of information has a unique name. And although it's not mandated, it's intended to be human readable, URL-like or URI-like name, slash separated. And unlike IP, which only has a notion of interface and a host, NDN has three kind of roles. So it distinguishes between routers, consumers, and producers. A router is, well, a router. A consumer is an entity that requests content. Content is never forwarded on a whim, just unsolicited. In order to get content, you have to request it. the entity requesting content is called the consumer. The entity producing content is called the producer or publisher. A given computer can be both a consumer and a producer, obviously. Theoretically, it can also be a router. Okay? But in the context of given interaction, there's a consumer and there's a producer. Whereas IP is simpler, right? The IP just has a host, an interface, or IP address, datagram, and a router. So a name is, well, here's an example. It's something like this refers to some segment of a video produced by Park. It can be arbitrary. There are no limits on its size. It can be short, long. And these are just suggested segments. Like it doesn't have to be exactly like this. And this kind of naming is very amenable to binary encoding, like each component has a length value pair. Okay. Yeah, and then there's segments. There's also an implicit hash, but I'm going to skip it for now. It's not germane at this point. Now let's look at specifically how NDN works in the network. This is where the interesting or the more important part of the process takes place. So the blue nodes are routers. Okay, so this is a simple network topology. The green nodes, and I'm sorry, I don't know if you can see it, but it says consumer. So the green nodes in this picture are consumers. The purple node is a producer. Okay, so we're going to witness an interaction. The consumer starts by generating what's called an interest. Right? This is a request for a particular content. In that interest, it specifies explicitly the name of the content that it wants to get. Okay? So it's not like an IP packet that has a source and destination address. This type of a packet has neither source nor destination. Okay? Does not have it. What it does have is the goal. What is the goal of this? The name of this particular content. The first hop router receives this interest and forwards it to the next hop using prefix-based routing. You know, like IP today uses longest prefix match based on IP addresses? Well, in NDN, it's much the same thing, except it's not longest prefix based on IP addresses, it's longest prefix based on names. So routing is in principle the same. So you see what happens. The first router forwards it to the next router, and the next router forwards it to the third hop router. Now you see the little green boxes that appeared in those blue circles. That indicates that every router that forwards a given content remembers it. It keeps what's called a soft or temporary state. So it remembers that, I received a request for this specific content and I forwarded it this way. Okay? It does it for several reasons. Eventually, the content will reach the producer. Now, mind you, in this case, in this example, in this slide, I assume that this content has not been requested before. So it is not in the network yet. So the producer will respond, assuming this is a valid request, right? It's a content that it has or can generate. The producer will respond. The content will follow in reverse, right? Like a pebbles, right? The path established by the preceding interest. So you see the little green boxes, it will follow the green boxes back. And in the process of following those green boxes back, the state will get flushed. Right? So it's like a one-time virtual circuit or a one-time publish subscribe kind of a thing. So now, but although the routers will flush the state corresponding to the interest, they will keep the copy of the requested content in a different thing called the cache. Okay? So on it goes with my primitive animation here. and then eventually consumer will receive its content, and consumer is happy. Okay, but notice that copies remain in the routers that processed the original request. Well, at some later point, a different consumer, right, maybe a little later, a different consumer requests the same content. The interest hops to the next router, and then hops to the second hop router, which happens to be the router that has a cached copy. So this request will not travel any further, right? And it will be satisfied by the content cached there. So the second consumer will experience a much shorter delay. And of course, less traffic on the internet side. So now you get, I think, a pretty good idea of how things work. Now, but whenever you have some really popular content, this could happen, right? But if it's really, really popular, things are not always this convenient. What in particular could happen and does happen is that this request from this consumer can occur while the first request is being handled concurrently. What then? Right? What then? Well, let's zoom in on a specific router. All right, so now we're looking into a given router, and that router has 4 interfaces, let's say. Okay, so, and every router has 3 things. Something called a PIT, pending interest table. That's the little green boxes you saw earlier. That's a table of interests that have not been satisfied. A content store, in other words, a cache, and a forwarding information base. That's a routing table, basically. Okay? So an interest comes in, you see, and is forwarded out. So it came in on interface 0 and was forwarded out on interface 2. So the router creates a table entry that says, oh, I received an interest for this content, and it came in on interface 0, and I forwarded out on interface 2. And then, if in the meantime another interest comes in for the same content, while the first one has not been satisfied, it is not forwarded further. What occurs is collapsing. So that interface, you see, that it came in on, interface 3, is added to the table entry. Why? So that when the content eventually comes back, it is multicasted to the interfaces that the interest came in on. So that's the second basic, let's say, congestion elimination, a congestion reduction property of NDN. All right, I already said most of this. I think the forwarding is pretty straightforward. There's nothing really new here as far as NDN routing is based on prefixes and reachability. In the interest of time, I'll skip it. This is, well, again, I'm sorry for my choice of colors, but this is the NDN testbed, and it just shows you that today you can actually see it. It's real, and it has, by now, this is even last year, so this probably has well over 100 nodes. Mostly in the US, but also overseas. Now, back to security. Now that if you're awake, you probably know a little bit about NDN, or enough to be dangerous. So, security. So now in today's internet, we secure the pipe, right? This virtual pipe between communicating endpoints. So information is good because it comes out of the right pipe. But in NDN, where information or content can settle in the network, right? And so communication is not always between a consumer and a producer in real time. Instead, as you can see, communication can be between a consumer and some arbitrary network cache. So now, integrity, trust, authenticity become properties of the content, not the pipe it comes out of, and should be sort of coming out of the content itself, which poses a big problem, because today's internet is focused on securing the pipe, and tools that we have, security tools we have in today's internet, like SSL TLS or IPsec, secure this communication paradigm, right? End to end. So if we want to get a content, and the content may be at its producer or at some random router, how do we do this three-way handshake that SSL TLS requires? Makes no sense. Even if it made sense, it would be tremendously wasteful, right? We would be doing this authentication handshake only to fetch one piece of content. So every piece of content we want to fetch, you'd have to do this handshake. Why? Total waste. So not a good fit for NDN. Because in NDN, content can come from anywhere. Which is nice, because if you're asking for popular content, chances are you don't have to go all the way to its producer. You can fetch it from somewhere nearby. But that makes some things difficult, right? For example, access control. Right? In today's internet, if you want something, you go to its source and you fetch it from there, and if that source decides to remove content, they remove it, it's gone. But once in NDN, once content is out in some router's cache, the source has no control. Okay? That makes things difficult. Also makes accounting difficult. If you want to count how many requests you have for content, you can't count from, when it's satisfied from some cache. So NDN does open up some interesting challenges. Now, since content can be retrieved from anywhere, how do we know to trust it? How do we know who produced it? How do we know if it's the right content? Well, NDN actually does offer some answers to this. And the main security feature of NDN, in fact, you can say the only security feature of NDN, is the mandatory presence of digital signatures in every content. In other words, every content must be signed by its producer. Okay? Not optional, mandatory. So, of course, every content must also have a name, right? Because otherwise it makes no sense. But name itself is not a purely security feature. That's a sanity feature. So it has a name, it has some data, right? That's the information it carries, and it has a signature. So, nice thing about digital signatures is this is public key digital signatures, because there are no other types of signatures. You can get integrity, right? Because if you use, as is the case today, most contexts, signatures used in tandem with cryptographic hash functions, you immediately get integrity. You get origin authenticity, right? You can authenticate the entity that signed it. You get correctness, because if you have origin authenticity and you have a name, you say, well, I requested this content, and, well, it came back. And then one of the sort of bonus features, or maybe it's let's say one of the features it has is that if you have content that's digitally signed, it can be verified by anybody who has a public key. Meaning it's not only the producer who signs and consumer who verifies, routers can verify content as well. Say, I don't want to forward it because it looks fishy. Bad digital signature, or bad producer. So. Now you can also restrict access to content, but that's an awkward feature of NDN. If you want to restrict access to content, you have to encrypt it. But encryption is easy to say, harder to do. Now, actual encryption is easy, but how do you distribute keys? That's a headache, so let's keep that in mind. Because while you cannot do access control on content because of caching, you can still do access control on the keys. But that presents this whole scalable key distribution problem. And then as far as trust model, well, as I said, content is signed, and you can look at the content, and given that you know the public key of its purported producer, you can verify it and get all kinds of nice features. But interests have no security features whatsoever, and for good reason. So remember, the interest is the type of packet that requests content. Interests contain the name, and that's it. There's some other auxiliary field, but it's, for all intensive purposes, just a name. No source, no destination. Also, NDN is agnostic to PKI, so it doesn't really specify what kind of infrastructure is to use. And it separates application-specific from network layer trust. So applications can have their own trust model, but network layer trust must be minimized for reasons I will explain in a minute. And NDN does offer a number of interesting privacy benefits. As I said, an interest has no source and destination address. That means if you eavesdrop on an interest in the middle of the internet, all you know is the content that it wants to fetch. You don't know where it came from, right? And you don't know where it's going. The reason you don't know where it's going is because although you see the producer, the name of the producer is somehow a part of the name of content, but you don't know where the nearest copy of that content is. It may be at the producer, or it may be at some router. So therefore, there's no destination, which is good for privacy. In reverse, so when replying with content, the content is being forwarded without knowing who requested it. If you follow the entire path, you get to know who requested it. But if we assume that we have adversaries that are not global observers, then you can't really tell anything from seeing some content traveling from one place to another. You just see, well, you know what it's called, you probably know who produced it, but you don't know where it came from, and you don't know where it's going to. Right? And also, this is an interesting feature. You may see a single interest, but that single interest may correspond to multiple real interests, right? Because of what's the feature you saw called collapsing. Also, by the same token, if you see a content traveling from, let's say, between two routers in the middle of the internet, that content may be serving one request or a much larger number of requests. So you can't really tell who wants it or how many want it. NDN also poses some challenges to privacy. Names are human readable, or supposed to be human readable. So if you do see an interest, or eavesdrop on an interest, you do know that somebody is interested in a particular content. So if you see something NDN, US, Wikipedia, STDs, herpes, well, and you say eavesdrop on the access point in this room, then you probably, you're reasonably well assured that somebody in this room is interested in herpes. And probably somebody has it, or knows somebody who has it. Maybe you want to move away from your neighbor, right about now. Same idea if you look at content, right? As content passes through or passes by, if you look at content, you may not be able to read the actual information. Maybe it's encrypted, but the name is not, right? Every content has a name. And so if you see a name like NDN Zimbabwe Pirate Bay blah 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 MP3, that's probably a pirated video. Maybe a good thing that you can see that, and you can maybe filter it out if you're an ISP, or maybe it's a bad thing because it makes censorship easy or easier. The other thing is signature privacy. You see, signatures is one of those classical examples of security versus privacy. Most people think security and privacy always go in tandem. They do not. A signature is a security feature. A signature is a very bad privacy feature, right? Because it tells you exactly who signed it. You might say, well, wait a minute, if you don't put the key there or certificate next to the signature, then you don't know who signed it. That's not true, right? If you have a signature, you can always guess the public key and verify your guess, right? Okay, guessing is harder than seeing, but still, you can verify that your guess is correct if you think that somebody in particular produced a signature. So the other problem is cache privacy. Turns out if you have a cache is a funny thing, right? So let's say whatever the access point is here, let's say the access point here is a router, right? So if I probe that access point, I can figure out very quickly if a particular content is in the cache of that access point, that first hop router. What does that mean? That means if I suspect that one of you, let's say, is looking at www.cnn.com front page, I can see whether there's a cached copy. How do I know? Well, it will come back very quickly, rather than going to all the way to CNN. Right? So that's caching, which is useful for scalable content distribution, which is being actually very unfriendly to privacy. Now, as far as security, NDN is very simple, right? In terms of security. They just sign everything and that's it. All content is signed. No need for any kind of handshakes and key distribution and signature verification in real time, right? Like with SSL or IPsec. Public keys are supposed to be a kind of content. Why? Because public keys are generally distributed in the form of digital certificates. But a certificate is a signed statement, typically by a CA, certification authority. But hey, what's the difference between a certificate and signed content? Well, clearly a certificate is a kind of a signed content. So public keys are considered to be just a special kind of content with a suffix key. So it's easy to handle them. And if you want somebody's content, you first pull their public key or request their public key. Once you get their public key, you can verify you can then pull their content and verify it with it. But of course, there are challenges. The state in routers, as I mentioned already with cache privacy, is kind of a blessing and a curse. It is a blessing because it's good for this scalable content distribution. It's a curse partly because of the privacy issue I mentioned earlier, and partly because the state can be abused via what we call flooding attacks. Right? So one of the kind of flooding you can do is interest flooding. Okay? And interest flooding is a kind of a denial of service unique to NDN, where an adversary generates a bunch of nonsensical interests. Now they're not completely nonsensical. The worst kind of an attack is the adversary says, I'm going to target Panos, and he has a particular namespace, that's /NDN/KTH/electrical engineering/Panos, and then he's responsible for that namespace, and I'm going to generate a large number of closely spaced interests or nearly simultaneous interests with the prefix that I just mentioned, concatenated with a random string. What's going to happen? The network sees a valid prefix, routes it towards Panos, but it's not going to find any cached copies in the network because that content is nonsensical. It's going to go all the way to him. He's going to look at it and say, this is junk. By the time he does that, the attack has succeeded. Because in the process, not only have I hosed him, I also managed to hose all the routers between me and him. And if I mount it as a distributed denial of service attack, I truly can cause some damage. The other problem is content poisoning, and it comes in two flavors. Content poisoning is essentially introducing into the caches of routers content which is not valid. Of course, if you're really alert, okay, and you've listened to me so far, you say, wait a minute, content is signed. How can you introduce bad, fake, poisoned content? Well, you can, because actually routers can verify signatures. But do they? Should they? Should routers parse public key certificate chains and look at expiration and revocation and deal with that nightmare of trust management? No, that would be nightmare. That would be worse. That would be the case of where a solution is worse than the problem. So most routers will probably not verify content, but will just forward it on the assumption it is good, which opens the door for content poisoning attacks. All right, then there are other issues. And so it turns out, and I'm nearing the last part of my talk, it turns out that content poisoning and trust management are actually very intimately related problems. So let's do a quick recap. NDN has three entities: producer, consumer, and router. Let's forget the router does everything I already mentioned. Producer does what? Announces name prefixes. So it says I am responsible for prefix such and such. Names and signs content. So it assigns unique names to content it produces and signs it. And then injects content into the network when it receives requests. It doesn't unilaterally reject anything. But when it receives an interest, it answers with content. Consumer generates interests, referring to content by name and receives content. Now, consumers are mandated to verify signatures. For consumers, signature verification is not optional. They must verify signature on every content they receive. All right. Now, I said, well, let's not ignore routers. So routers do all these things, like they route interest based on name prefixes. They remember where the interest comes from. They cache content. They don't have to cache all content, by the way. Right? They are assumed to be caching, but the decision of whether to cache or not to cache specific content is up to an individual router. And this is important. They may verify signatures, but are not mandated to do so. So let me skip this. So the problem, because I don't think we'll run out of time if I do go over it. How much time do I still have?
I think we can keep going.
Yeah? 40 minutes? Yeah. Okay. All right. So the problem I'm going to focus on is this content poisoning that I already mentioned. Right? So NDN's objective is scalable distribution of content, and it's facilitated by the caches and these PITs, pending interest table. Consumers verify content signatures, and when the consumer verifies a signature on a given content and says, oh my God, this content is invalid, what do I do? You have a problem. How can a consumer cause a router not to give it back the same content? Right? So the consumer says, oh, this is bad, let me request it again. Right? Well, that's dumb. Because if it requests it again, it's going to receive a cached copy of the same thing. So how would the consumer complain? So I don't like this is bad. Well, NDN allows what's called exclusion. You can receive content, and then if you don't like it, or if it could be stale, simply not bad, just stale, you can exclude it using a hash exclusion by hash. Sort of a clunky feature, but it doesn't solve the problem. Because if I receive a bad content and I exclude it in my next request or my next interest, clever adversary will simply introduce another piece of fake content. So I'll have to exclude that as well. And so on, and so on, and so on. Not good. Let's see. You could imagine that a host or a consumer could say, oh, I complain about this content. This is bad. Please flush it. Please don't give this to me. Well, let's think about this. So if a consumer complains to a router, we already have a problem. Right? Any networking architecture that allows a host to talk to a router opens a door for really bad denial of service attacks. That should not be allowed. Moreover, if we ask the consumer to flush the content of a given router's cache, even if that communication in itself is not a denial of service attack, then the request to flush something is a denial of service attack, because a bad consumer could make a router flush good content. Or if a router is not very trusting, a router would say, I don't trust this request. Let me verify a signature on this content. That's another denial of service, right? Because verifying signatures is expensive. So if a router, as a reaction to each complaint, will start verifying signatures, we'll have havoc. Okay, so that doesn't work. Because verifying signatures is expensive, and it is in and of itself a kind of a denial of service attack, right? So what we have is a problem where we cannot even authenticate, right? So we can say, oh, well, wait a minute. If you take a security course, you say, wait a second, you haven't covered all possibilities. Maybe if a consumer decides to complain about a bad content, we should authenticate the consumer's complaint. Another denial of service attack. Again, authentication requires a cryptographic operation on the basis of what? Well, you cannot use symmetric cryptography, so you have to use public key cryptography. So authenticating consumer's complaint is just as bad as verifying content signature. So we're hosed, right? Because we have this problem that authenticating a consumer also contradicts, by the way, or goes against the privacy feature, right? So if the routers now authenticate consumers, they suddenly get to find out who requests given content. And that goes against that privacy feature of NDN, where interests are not supposed to carry source and destination addresses. So that is an interesting problem. Now, as I said, a key in Indiana is assumed to be a public key, is a kind of a content of itself, a certificate, and it contains authorized name prefixes, right? So, so in case of Panos, it would contain his namespace, right? He can arbitrarily extend it, but the prefix is fixed, right? There'll be something like NDN, Sweden, KTH, EE, Panos, blah, 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 blah. And then he can append anything he wants to that and issue content. So, sorry, maybe you can see this. Actually, it's like /CNN/USA web key, or this is VeriSign Europe key. So you have these names for keys themselves. Well, content poisoning occurs for several reasons. First, you have ambiguous interest. That interest can specify a name, but it doesn't know what content will come back. Right? It's a chicken and egg problem. If you might know the name of what you want, like /world/CNN front page /US. So you want the front page of the US news for today. But what the content that will come back differs, right? Depending on time. Today it will be different from the one tomorrow. There's also no unified trust model. Some applications will have hierarchical trust, many will, and some applications will have peer trust. And some applications will have some kind of hybrid trust model. And there's no unified trust model at all. It can't be. And also applications change, right? We have new applications come in, old ones go out. Also an application might change its own trust model over time, which makes it a big headache. So we move on to the following axiom, that actually we cannot solve the problem of content poisoning without addressing the problem of network layer trust. You see, that a router is essentially asked to do an impossible thing, to forward content somehow on the basis of some nebulous trust. It should not forward fake content, but how does it know fake content from good content? And so, if routers, as I mentioned earlier, if routers start doing complicated things like parsing PKI hierarchy, public key infrastructure hierarchies, fetching CA public keys, verifying expiration time, revocations status, we'll have a total nightmare. Right? You don't have to be a security expert to realize this is crazy. A network layer entity like a router in the middle of the internet, or even at the edge of the internet, doing these kinds of activities is an anathema to networking people and should be an anathema to security people. So you should not do things like verify public key certificates or fetch them, right? If a router receives content that has a public key of Panos, but it does not know public key of Panos, and it doesn't know the public key of KTH, what is it going to do? Hold on, verify, wait with verifying content until it fetches the public key of KTH, then fetches public key of Panos, then checks the expiration and revocation, and only then verify content. Then the whole communication will grind to a halt. So ideally, and this is my sort of thesis here, a router that decides to protect itself against content poisoning should perform at most one signature verification per content. If it does none, then content poisoning will persist. But if it does at least one, maybe we have hope. And so our approach is based on this, it's a US thing, the KISS principle. So depending on the inflection, there's two ways of saying it. There's keep it simple, stupid, meaning keep it simple and stupid. Or if you're, another way is less polite, keep it simple, stupid, referring to somebody you're talking to. I prefer the first. So our approach is keep it simple and stupid. Right? Straightforward. And we achieve this, or I claim we achieve this, by a very simple rule. And the rule is called IKB, or Interest Key Binding Rule. That is, whenever a consumer generates an interest for content, the consumer must refer to the public key of the publisher of that content in the interest. I say refer, I don't tell you how. Okay? But imagine that every interest now unambiguously refers to the public key of the publisher of content. Now, what that does, okay, what that does is it conveys to every single router that processes that interest some function of the public key. Maybe the actual public key, or maybe a hash thereof, okay? And now, when the content travels back, hopping around in reverse along the path established by the preceding interest, every router can say, aha, I don't care about the public key infrastructure, I don't care about any expiration or revocation or anything. All I care about is that the public key that purports to sign this content corresponds to the public key that the consumer specified in interest. And a router can perform this simple check. It doesn't take any crypto. But if a router wants to be sure, then it would take the public key and verify the signature, as long as it's the right public key. And so that's our approach in a nutshell. Okay? It frees the routers, and really it's the only interesting feature is that it frees the routers from being concerned with any kind of public key infrastructures or trust that is specific to the application. Just says, consumer wanted this public key to be signed, to be signing this content. Does it? Yes. Go. Does not? Throw it away. That's it. And so, in more detail, we use actually an already existing field of NDN interest called PPKD, or Publisher Public Key Digest. So we actually don't put the public key itself, but we say, well, the consumer who requests content will hash the public key and include the hash in a special field in the interest. And that will be cached in this pit. Remember, there's little green boxes that will be cached by each router. And so you already know how the router will verify things on the way back. Now, maybe you're thinking, again, if I haven't bored you to tears yet, you're thinking maybe, how would the consumer get that key? Isn't this a classical example of chicken and egg problem? How would the consumer get the key of the producer of content that it wants to fetch? Well, there are several ways. One is to imagine that you have pre-installed root keys, kind of like what we have today with browsers. When you install your favorite browser, it comes with these roots of trust. Used to come with a few, now it comes with tons of them, but it comes with some roots of trust. You trust, presumably, at least the place where you fetch your browser, right? So if you go to Google and get Chrome, you trust that. If you go to Mozilla, you will trust that you're getting Firefox there, but when you install it, it comes with some roots of trust. So you can imagine NDN doing the same. So the end user or the consumer side installation will include roots of trust. And then the rest is easy. Right? Because you can start pulling keys one by one, walking down or the hierarchy as needed. Another way is a global search-based service. This is, imagine something like Google, but for keys. So you enter Panos and KTH, and Google, or some Google++, returns to you the public key of Panos. So now you have the public key, you can fetch content. Or you can imagine something similar to DNS. Today's DNS has issues, certainly, but it's been working, right? So and there are security extensions for DNS itself. But imagine something like a key name service, right? Not domain name service, but key name service. You enter a prefix, right, a name, and you get back the key. And this KNS would be some of the separate enabler service like DNS today. Right, so not very difficult. The producer is required to include the public key along with each content, but that's not a big deal because the producer is already required to include a signature. Including a public key is not a big burden. In fact, an optional locator field already exists. And what do routers, and this is the most important thing, what do routers need to do? Well, a router must match the key locator field, right, in the interest, in the content to this PPKD field that arrived in the preceding interest. That's just a simple matching operation. And then if it chooses to, it has to verify a signature. So if the match doesn't pass, it doesn't need to verify a signature, just throw it away. If the first step passes, then it verifies the signature. But I emphasize again, no fetching, storing, or parsing or verification of public keys themselves. Routers do not do that. And so is this secure? Well, we have some kind of a semi-formal analysis of this approach that says, look, if everybody adheres to this interest key binding rule, then you have no content poisoning. Okay? Under the assumption that, of course, all nodes abide by the rule, consumers are not malicious, consumer-facing routers are not malicious, consumer-facing routers are routers next to the consumers, and the logical, or the link between the consumers and nearest routers is not compromised. Now, you might think this is a lot of conditions, but it's not, because if a router next to the consumer is malicious, no matter what you do, you can always introduce fake content. Okay? So, we can show this, so I won't bore you with details, but I can point you to a report that describes this. So, is it secure? Well, let me just hand wave in the interest of time that we think it is. There are some optimizations, because even with this approach, a router that wants to protect itself against content poisoning would have to verify, perform one signature verification for every content it forwards. This is obviously not cheap, right? Even with the fastest RSA signature implementations. It's not cheap, and it's something that routers don't normally do, right? Routers are there to forward packets, not to do security, but we can't avoid it, right, if we want protection against content poisoning. So we imagine that only border routers would implement this. Right? If you have the, let's say, intra-AS or intra-domain routers, they don't need to do this. So only routers at the border of a given autonomous system would have to do it. And at the very least, routers that are like at ISPs or consumer-facing routers would do it. But others won't. Or won't necessarily have to do it. Let's see. So there are other optimizations. The important one is something called self-certifying names. So here the approach is the same as before, except now what we want to do is imagine the following, like a web page, right? So your main web page, let's say CNN. Okay, so the front page, you fetch that front page and as a piece of content, and then off of the front page they have links to individual articles. That's a typical way of structuring web pages. Well, when the consumer is fetching the front page, he doesn't know its contents, he doesn't know anything about it. But when he fetches the front page and gets it, the links to individual articles can actually contain the hashes of those articles. Right? So in a way, CNN would be signing the front page, but with the front page, it would also be signing indirectly the articles that are linked off the front page. And so what allows is a very trivial optimization. Now if a consumer wants to fetch an article that is pointed to by the front page, let's say, I don't know, something happening in, Podunk, Iowa, then it actually doesn't need to fetch that article by name only. It can actually fetch it using the name and the hash. Now if you remember the very beginning of the presentation, I showed you an example of a name and I said there's like an implicit hash there. Well, you can make it explicit by appending the hash of the desired content to the end of the name. That has the following effect, that now the router that will forward the content will compute the hash and make sure that the hash matches the one you specified in the interest. So the only cryptographic operation required of the router is a hash computation. But in NDM, hashes are already recomputed by default by all routers. So actually, it costs almost nothing. It actually costs nothing extra. So you see, this is a trivial approach. It's called catalogs. You can imagine this as a generalization of this would be Merkle hash trees. Right? But any data structure, any authenticated data structure that allows this kind of indirect signing will facilitate this optimization. Anyway, I will save you from further details. Now, there are essentially, well, at least in this context of trust management or network layer trust, we distinguish between two types of content. First is like distribution, right? Or two types of traffic. Content distribution, like video streaming. So with video streaming, if you're getting like a YouTube video or Amazon Video. Imagine that you're requesting this content, but it's already available. It's not produced in real time. So actually, catalogs, this approach with catalogs is very useful. You first get like a signed content that contains, let's say, individual chapters of a video or individual segment. You verify the signature on that, and you don't need to verify any more signatures because all the chapters are essentially included. Right? And you can effectively use the catalogs. Or the browsing example that I already gave you with CNN. But not all traffic falls into that kind of convenient category. What about interactive traffic, right? So if you're watching like a real-time sports event, or if you're doing a Skype call or some kind of voice over NDN or something like that, then you cannot use the catalog approach because content is produced in real time. So then you just fall back to the approach I described originally, which is just using the public key, right, and performing a signature verification. Okay, so we're almost there. We're almost done, and I see that some of you are awake. That's good. So the next step will be actually to build this stuff, and we're in the process of sort of prototyping parts of this architecture and experimenting with catalogs as self-certifying names. Our collaborators at Park have implemented a version of this kind of key name service. We haven't done any application-specific bootstrapping of trust. That's for next few months, and then we haven't also figured out how to isolate malicious routers, right? So if you have content poisoning in the presence of compromised routers, that still remains an open question. And here are some references. Of course, they're way too small for you to see, but I'll be happy to distribute copies of the slides via Panos. Thank you.
Questions for Gene? I will let him handle the questions.
So it seems you're setting something up which is very easily used for censorship. I mean, you could say that the routers only allow certain producers or things like that. So if you have control of, say, the majority of routers, then you can control exactly who produces content. Is that a worry, or could you do some kind of game theoretic analysis?
All right. So first of all, that's outside trust management, right? The topic of today talk, but yeah, very, very good question. And nonetheless, yes, I did admit, right, that you have this privacy issue that the content clearly tells you what it is, right? Today, if let's say your router here at university wanted to filter certain content, you would have to filter it on the basis of IP address. You have to do reverse lookup, right? Based on a source IP address, and say, oh, this is coming from North Korea, forget it. Or it would have to do deep, deep packet inspection, right? Okay, this looks like porn. Okay, forget it. And in the end, the job of the censor is easier. So, yes, you're right. My answer to that is use anonymous communication. So like in today's internet, if you want privacy and censorship resistance, you would probably use something like Tor. And we have actually something close to Tor, which is something called Andana, which is basically an analog of Tor for NDN. Now it differs from Tor because Tor establishes a circuit. So Tor is still an example of this secure the pipe approach. Nobody knows how the pipe snakes through the internet, but it's still the pipe, right? In NDN, our approach is to have the same kind of idea with anonymizing routers, but you don't build a pipe, you kind of build a very ephemeral circuit, right? So that's my long and short answer. Yes?
So, I really like the talk, but I have some questions. I'll try to have only one actually. The main problem with credential management is how do you revoke keys? And the problem is that when in the traditional networks that we have right now, we have one producer from which we'll get the content and has the key. So it's really easy once this server is compromised, for example, to say, okay, the key is not valid anymore, don't use it. But now what's the problem in what you described? That the content will be within the network at places that we don't know, but we can get from. so we cannot revoke the content. We can revoke the key of the producer, but we cannot revoke the content. So this creates a vulnerability window within which the adversary that has compromised the server and has the private key will start signing content and consumers will receive it.
That's right. That's right. But I claim, I mean, so your assessment is correct. I just disagree with the fact that it doesn't exist today. NDN does not change the picture very much. But let me explain one thing. Revocation and management of certificates, etc., is consumer's responsibility. Not producer. Producers, let's assume, may be stupid or malicious or both. But consumers should be vigilant, right? So we say that consumer must be the one periodically checking revocation, fetching fresh public keys, and if a producer's public key has been revoked, let's assume the consumer is vigilant and obtained the new public key. That consumer will not get poisoned content because it will, using the approach I described, will specify the hash of the new public key in its interest request, and therefore any old, stale, invalid content that may have settled and still exists in the routers will not be returned, unless the routers are malicious themselves. Do you see? Okay. Yes, please.
So you're calling you're finding your stuff by content,
Yeah.
and you're returning your stuff by path, if I understood you correctly.
By name, right? So you're looking for it by name, yes, and you're returning it. You're hopping back.
The path that you arrived at.
Yeah.
Why don't you return by name?
Meaning a consumer
The name of the
of the
entity
requestor.
that originated the request, for instance. That it would be harder. There would be cache misses. Sure.
Yes.
But it seems
The
like
problem is that the name has a unique kind of a purpose here. It refers to content, not an address, not the location. And so if you,
necessarily, but it could be me. You know, I mean, I could make a request for some data, and then before I receive the reply, I move to another room, and instead you're propagating the answer back along the path which is no longer valid.
this is true. So let me answer a side question, not exactly the question that you asked, but that kind of emanates from it, which is mobility, right? So what happens if you move to another room while your interest is being served by the network and so on?
That's part of the question.
Well, so let's assume they do move to the other room, so you've actually changed, let's say, first hop routers. You would have to reissue your interest because obviously your content will not come back to you because the first hop router where you were before would broadcast it on the segment and you wouldn't receive it. Right. So you would have, having moved to the other room, would have regenerate the interest. But now the second hop router would have the content and it will come back to you way quicker than it would other. So it's still not optimal, right?
Sure.
Your suggestion is why don't you use your name? Now, my statement here is that wouldn't be a name as a name of content. It would be an address. It would be an address. So why don't they do that? That's a networking question.
It's a content just as much as a public key is content.
But a name of an entity is not the same thing as content. That's what NDN claims, is that content refers to information. Your name is not information in and of itself. There's no signed information corresponding to your name. However, one could imagine an architecture that just has two types of names. One name is for content and one name is for address. There is no mutual exclusion here, fundamentally. You could do that. Perhaps a better answer can be given by a real networking person rather than a security person pretending to be a networking person or wearing a hat for the day. I think it could work. The problem is that privacy, the first thing I notice here is that, of course, somebody looking at the interest would know where it comes from, mobility notwithstanding. And that's something that NDN tries to avoid. Is it a huge problem? Maybe not, maybe not. It's another point on the designs page, you know. Yeah. Any other questions?
So I think we have to close
All right.
here because of the next seminar and the broadcasting. So thank you very much.
Thank you.